All right, so now we're going to talk about semantics, and this means learning the truth tables for the operators. So we've been talking so far about how to make well-formed formulas, which essentially means how to construct them, but we haven't been talking really much about what they mean, which is what we're going to do now, and that's called semantics. The theory of meaning is semantics versus syntactics. So the semantics of propositional logic mainly focuses on the meaning of the logical operators. That's the only thing that really has intrinsic meaning in propositional logic. And we do this with this really beautiful invention that we call a truth table. So first of all, it's important to understand from the beginning something that you might be assuming, that there's only two truth values. We call them truth values. The two truth values are true and false. This is pretty commonsensical to most people, but it doesn't have to be that way. There are logics that have multiple truth values. There's even logics that have an infinite number of truth values, like fuzzy logic, which thinks of truth and falsity in terms of degrees, the amount of truth in a proposition. So something you say might be 60% true and 40% false, for example. But we don't do that here. So true and false, we keep it simple. So the operators we use in propositional logic have an interesting property, and we call that property truth functionality. These are what we call truth functional operators. And what that means is that anytime you give a particular assignment of truth values to a proposition, to the constituent propositions, you get a definite truth value as a result. So, for example, if you think about and you say, well, P and Q, then no matter what the truth values of P and Q are, say P is true and Q is false, P is true and Q is true, etc., there's going to be one definite truth value for the whole statement P and Q. So there's no way you can have no truth value, and there will be no deviation. It's not like sometimes it'll be true and sometimes it'll be false. All right, so let's go ahead and define the semantics for each of our operators. So negation is the simplest and the easiest because it only has two possible values. This is a nice way to learn how to read a truth table. So you'll remember that we use phi and psi when we're being careful to indicate when we're using the meta language and talking about propositions rather than using specific ones. So what the truth table for negation says is that when phi is true, right here, then not phi is false. And when phi is false, then not phi is true. Okay? So one way we can say this is that negation is a truth function that converts the truth value of a proposition to the opposite value. So not turns true into false and false into true. So if I have a proposition like I am hungry, if that's true, then it's not the case I'm hungry is false. All right? Okay, so with conjunction, we have a larger truth table. It actually has 4 rows. And the reason for that is that it's what we call a binary connective. It connects 2 propositions together. And in general, you can have connectives that connect more than 2, 3, 4, 5. Essentially, what we can say is that if however many propositions are being connected, you'll have 2 to that number of propositions in the rows in the truth table. So there's 2 to the 2, which is 4 rows, because and the other connectives connect 2 propositions together. So with and, you have 4 possible combinations. You could have phi is true and psi is true, phi is true and psi is false, phi is false and psi is true, and phi is false and psi is false. And what the truth table for and tells us is this, that if phi and psi are both true, then and is true. Otherwise, it's false. So the truth table for conjunction represents this fact that a statement of the form phi and psi is true when psi is true and phi is true and psi is true, and false otherwise. So that's pretty easy to remember. The only time you're going to be writing true is when phi is true and psi is true. And all other times you're going to be writing false. All right, now, intuitively, both negation and conjunction work pretty well. The truth table for negation reflects the way the word not is ordinarily used in English. It doesn't reflect every usage. Sometimes we say no in an ironic way, like no, which actually means yes. And also in some languages like Spanish, a double negation, not a, would still mean a, and that's not the case in English. It's not the case in English, but it's also not the case in propositional logic. Every time we add a negation, we change the truth value. So not a actually means the same thing as a in propositional logic. Now the truth table for and also reflects the usual way of using the English word and. But there's other ways of using the word and too that it doesn't capture, and we're not trying to capture. So for example, when we say Fred got in his car and drove home, well, that typically means Fred got in his car and then drove home, then meaning afterwards, right? And that's turns out to be a really complicated and very different statement. Our and doesn't have anything to do with the temporal, the time order of things at all. So the important thing to understand here is in each case we're introducing a very specific meaning for the operator that isn't necessarily the exact way our intuitions tell us these operator means in English. In fact, English is just so much more complicated than propositional logic tries to capture. Okay, well, this is disjunction, or, and what the truth table for disjunction tells us is it's kind of the opposite of and. It represents the fact that a statement of the form phi or psi is false only when both phi and psi are false and true otherwise. So with in conjunction, the only time you write true is when they're both true. In disjunction, the only time you write false is when they're both false, when both of the constituent propositions are false. Now, as we indicated earlier, in logic, in propositional logic, in logic generally, we use the inclusive sense of the word or. And this means that a proposition like phi or psi gets assigned the value t when phi is true and psi is true. So if we were to try to capture the truth table for the exclusive or, which we're not going to do, but just to show you what it would look like, we would be, and if you remember, the exclusive or is when we say either or, and what we mean is not both, right? So in that case, this would be the difference. True would be false. And that's a perfectly good truth table. It's a perfectly good operator, but we just don't use it, as we explained earlier. Anytime we want to capture that, we just capture it using the inclusive or and a negated conjunction. Okay, now the conditional ends up being a little weird. It's straightforward. The assignments are straightforward as far as memory is concerned. As memorizing them, it's not a big challenge, but it's a little bit. It's quite a lot actually less intuitive. So this is the truth table for the conditional, and what it tells us is that there's only one time when a conditional is false. So again, similar to and in this sense, but the time that it's false is a different time. It's when the when the condition when phi is true and psi is false. So conditionals, as you know, are statements of the form if phi then psi. And although we haven't stressed this yet, the if part, if psi, is called the antecedent. So if I talk about the antecedent of the conditional, I'm talking about the if part, and the then part is called the consequent. Okay, so there's the antecedent and the consequent. And so the truth table says that the only time a conditional is false is when the antecedent is true and the consequent is false. In all other times, the conditional is true. Now, if you think about an English statement like this, if you keep staring at me, I'm going to bite you. Well, think about the truth conditions of that. If I keep staring at you and you just bite me, well, it makes sense that what you said is true, right? I mean, I kept staring and sure enough, you bit me. So it makes sense that we would assign true to that statement. And also, if I keep staring at you and you don't bite me, then I'd say that your statement was clearly false. Look, I kept staring and you didn't bite me, so what you said was false. That's intuitive as well. So the first and second lines of the truth table for the conditional are in fact very intuitive. The last two lines of the truth table, though, are not intuitive, and there's no way that we can just make them clearly intuitive because English uses the conditional quite a bit differently. So all we're going to try to do here is make it clear how we're using the conditional in propositional logic. So the reason that it's not intuitive is that the last two lines where the antecedent is false is not intuitive, is that we don't care really about the truth value of a conditional statement when the antecedent condition is false. So suppose you say, if Butch asks me on a date, I'm going to say no. All right. Well, what if Butch doesn't ask you on a date? Is what you said true or false? Well, most of us would say when we think about this is that we don't know or we don't care. It doesn't matter, or both. We don't know and it doesn't matter. There's just the question never came up because Butch never asked me on a date. Well, look, that's okay in English, but it's not okay in propositional logic because the operators are truth functional. We need an answer to this. We have to put some value in for the cases when the antecedent of the conditional is false. So given this stipulation, the next question is whether it would make sense to fill out the table differently. So for example, would it make sense to say that the conditional is false whenever the antecedent is false, which is how we've filled it out here? Would this make sense? Well, look, we could do that, but it's interesting to think about what we would have done if we had, right? This says true, 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 false, 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 true, false, 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 false. Now, what truth table is that? Well, that's already the truth table for and, right? And that doesn't get us anywhere. Why would we just make if, then, and mean the same thing? So that wouldn't make any sense since it's just the truth table for and. There's no point in having two different operators that mean the same thing. So where do we go from here? Well, there's an interesting connection between the arrow and the wedge disjunction, which can help us see the virtue of the original assignment of truth values to the arrow. So consider the proposition, if I eat breakfast, then I am happy. If I eat breakfast, then I am happy. Well, think about this in terms of disjunction. And what you'll realize is that if I eat breakfast, then I am happy means the same thing as either I don't eat breakfast or I am happy. Now that might not be totally obvious to you immediately, but just think through it with me for a second. The first one says, if I eat breakfast, then I'm happy. Given that I eat breakfast, I'm guaranteed to be happy. So, look, either I don't eat breakfast or I do eat breakfast, in which case I'm happy, right? So either I don't eat breakfast or I'm guaranteed to be happy. Either I don't eat breakfast or I am happy. So these two statements have exactly the same meaning, even in English. Well, what that means is that if A, then B should mean the same thing as not A or B. If I eat breakfast, then I am happy. Either I don't eat breakfast or I am happy. They should mean the same thing, which means that if we did a truth table for if A, then B, and we did a truth table for not A or B, they should have all of the same values. They should coincide completely. And it turns out that the truth table for the disjunction, not A or B, using the values we've already agreed make sense for the inclusive sense of or, produce exactly the same truth table as the standard assignment for if A, then B. So if you look at these two truth tables, you can see something pretty interesting. The one on the left is just the truth table for the conditional and the standard assignment, the one we're trying to make sense of, really. And the one on the left is just the truth table for not A or B. So if you look at the truth values under B, in both cases, they're exactly the same. If you look under the truth value of A, they're exactly the opposite for A and not A as they should be. So where A is true, not A is false, true, false, false, true, false, true. So what this does then is give us an assignment of truth values that are exactly consistent for both. And what you see is that the truth values under the standard assignment of if A, then B match identically with the truth values under not A or B. And you can think through this now because you know what the assignment for values for disjunction is supposed to be, which is that disjunction is only false when both of the disjuncts are false. So false true has to be true, false false has to be false, true true has to be true, and true false has to be true. Okay, so they're both the same, which means in logic that they both mean the same thing. That's actually what we mean in logic when we say that two propositions mean the same thing. We mean that they're logically equivalent, which means that they have the same truth value under every possible interpretation. strictly speaking, by the way, I should have been writing psi and phi here. Sometimes I'm going to just use italicized English letters to indicate the meta-language rather than the Greek letters that the book uses, just because I think sometimes it's just more intuitive when we're discussing something a little more complicated. Okay, here's the truth table for the biconditional. This is the last one. The biconditional is true when the constituent formulas phi and psi are either both true or both false. So when they have the same truth values, then it's true. When they have different truth values, then it's false. And that's pretty easy to remember as well. The simplest way to understand the truth table for the biconditional is that we want A if and only if B to mean the same thing as this conjunction. So when we say A if and only if B, we mean if A then B, right? It's going this way. If A then B, and the other way. If B then A. If B then A. So we don't have a symbol that's written like this, right? That's not one of our symbols. So, but that's essentially what we're doing when we create the biconditionals. We're saying, oh, it goes back the other way too. So if A then B and if B then A is what this should mean. And so it turns out that we're not going to do it right now, but if we were to go ahead and do a truth table on that whole proposition, it would have exactly the same truth values as A if and only if B, which is a good thing. That's what we want, which is what I say there. Okay, so to wind up, you might find it kind of confusing to think about the relation between the truth functional connectives that we use, the operators that we use, and the ordinary English words that we've sort of stolen them from. And the good news is that you really don't have to. You don't have to think about this stuff if you don't want to. The only thing you really have to do is learn what the truth functional connectives in propositional logic mean. And this really means you've got to learn the truth tables and you've got to learn them cold. So this is kind of the easiest memorization task you're going to have, but this is what you need to do. If you need to be able to look at a blank truth table and be able to fill it out. So that's your task for after this lecture, is just to be able to write these truth tables out very quickly so that you can go on to the next one and actually do a little work with them with the truth tables in your head. Okay, that's it.